Hello, in this video we're going to take a look at a couple of examples of Newton's method. Newton's method is one of a whole family of methods to find approximations to solutions of equations. If you want to learn more about these methods, look up numerical analysis. We offer several courses in that subject at Iowa State. Many of you in engineering will need to be very concerned with methods like this that approximate solutions of equations. So this method is set up to find approximations or roots to equations of the form f of x equals 0, where f is a differentiable function. We will need the derivative to do this. So many calculators have root finding algorithms on them. They work very well, so why do we need to know anything about Newton's method? Well, there's a couple reasons. Calculators and computers use a variety of approximation methods to solve solutions of equations. Newton's method is one of these. It's used on some calculators. And by understanding how the method works, you'll better understand conditions under which the solution methods can be applied, and you'll better understand what might be happening when the solution methods don't work. There are times when they go wrong, and you can see some examples of this at the back of section 4.7 in your textbook. Secondly, it's a nice example of what's called an iterative method or an iterative process. Many of the algorithms used by engineers and scientists are iterative in nature, and iteration is also an important idea in mathematics and one that'll show up a lot in Calculus 2 and in differential equations. So we're going to demonstrate Newton's method by finding approximations to two different equations. We'll start by seeing how we can use this method to approximate the cube root of 10. So there's our problem. Now, the cube root of 10 has the property that if you cube it, you get 10 back. So we can find this value by solving, or actually approximating, a solution to the equation f of x equals x cubed minus 10 equals 0. So one of the roots, at least the real root to that equation, the real solution, is the cube root of 10. Now, to use Newton's method, we start by making a rough guess to the desired value. It doesn't have to be a great guess, but of course the closer you get on your initial guess, perhaps the faster you'll get to a solution or an approximation you can live with. Now it's not hard to see the cube root of 10 is between 2 and 3, so let's guess x0 equals 2. And we're going to use the label x sub 0 because this is going to be the first in a sequence of values or iterates, x0, x1, x2, x3, etc., that we can produce. And each of the elements we produce will be closer to the solution or to the number cube root of 10 than the one before it. Newton's method tells us how to generate the terms of this sequence one after another. Now, according to Newton's method, we can get the next term in the sequence. Remember, x0 is 2, we start with that. Newton's method says the next term, x1, is given by calculating x1 equals x0 minus f of x0, and f is the function we have already defined here, x cubed minus 10, and then divided by f prime at x0. Usually want to take care to make sure that that value is not 0. And if x0 is 2, this is 2 minus f of 2 over f prime of 2. So we're going to have to take 2 and plug it into the equation for f, the formula for f, to get the numerator, and into the derivative to get the denominator. Okay. These are easy calculations. If we put in x equals 2 in the f equation, we get 2 cubed minus 10. There's the numerator. And the derivative of x cubed minus 10 is 3x squared. And so here is the calculation, f prime of 2 on the bottom. A little arithmetic, that comes out to be 13/6, or about 2.1667. Now, Newton's method is working. This latest value, x1, should be closer to the cube root of 10 than x0. Of course, not hard to check that with our calculators. We see x0 cubed, 2 cubed is 8. That doesn't come out to be very close to 10. But if we look at x1 cubed, again, about 2.1667 cubed, we get 10.1718. So that's quite a bit closer to 10. We'll do one more round of this to see if we can get even closer. But before we find x2, the next term in our sequence of iterates, we're going to look behind the scenes and see that the value x1 came from just some very clever work with the tangent line. So let's take a look at the graph of y equals x squared, x cubed minus 10. There it is. This graph crosses the x-axis at the point cube root of 10. Of course, that's the number we're trying to find. So that number is kind of graphically illustrated right there. We've plotted our initial guess, x0, and the f value that goes with it, f of x0 or minus 2, as shown by the dot on the graph. Now what Newton's method does is it computes the tangent line to the graph at this point, x0 comma f of x0. That's right there. We've done a lot of tangent line calculations. We know at the point x0, the tangent line is given by y minus f of x0. So that's the given y coordinate. And that's equal to the slope, which is the derivative f prime at x0 times x minus x0. So this point is the x0 f at x0. And in this case, that is just the point 2 comma minus 2. So if I put these values into the tangent line equation, we find that this equation here in 2 is really just this down here. Y plus 2 equals 12 times x minus 2. Now, the value x1 is the point where this tangent line crosses the x-axis. So in this picture, we can see x1. Well, can't really see it. It's pretty close to the, but it's right about there, right where the tangent line crosses the x-axis. Now, when that happens, the y value of the tangent line is 0. So we put 0 in for y in the tangent line equation here, and solve for the x value, which again we're calling x1. That's x1 there. And so we end up solving this equation. So 0 minus fx0, because we want y equal to 0, is the slope f prime x0. And then the unknown point we're trying to find, the axis crossing point x1, and then minus x0, which again was this given x value from the point x0 comma f of x0. Little algebra, and if we divide through by f prime at x0 and add x0 to both sides, we get x1. Here it is. Of course, that's what we saw that before. That is the Newton's method formula that gets us from x0 to x1. And as we saw earlier, this gives 13/6 when x0 equals 2 is used. Now finally, let's zoom in on the graph to get a better look at what's going on here. So now we have over here, here is that point 2 comma minus 2, or f of x0, or x0 f of x0, as we talked about down here. And the tangent line is in yellow, and the graph f of x equals x cubed minus 10 is in blue. And so we can see the tangent line stays pretty close to the graph. We studied that when we looked at differentials back at the end of chapter 3. Tangent line stays close to the graph. So where the tangent line crosses the x-axis should be pretty close to where the curve crosses the x-axis. And of course, that's the numbers cube root of 10 we're looking at. So that's all Newton's method really does, is it makes use of two ideas. First of all, the tangent line is close to the graph. So when the tangent line has y coordinate 0, that should be pretty close to where the graph has y coordinate 0. And it's much easier to work with lines and solve equations for lines than it is to work with cube roots or even more complicated equations. So let's do this one more time. If we need a better approximation than x1 equals 13/6 to the cube root of 10, we can perform Newton's method once again. This time we let x1 play the role of x0, so that's our input, and the output will give x2. So our calculation would look like this. Again, here's the Newton's method updated from input x0 to input x1, right there. x2 is x1 minus f at x1 over f prime at x1. And since x1 is 13/6 by our previous calculation, it leads to this result down here and a value now of about 2.1545. Again, I just used a calculator to do all these calculations down here. Is that close to the cube root of 10? Well, you can try it. Let's take this x2 value, cube it, and we get this impressive fraction out here. And when you put it in decimal form, there it is, 10.000960. That's coming out very close to cube root of 10 then after just 2 uses of Newton's method, so that's not too bad. If you wanted to do even better, of course, you could take this number, the 3277 over 1521, our x2, use that as input into Newton's method, find x3, and keep going until you're satisfied with the degree of your approximation. Take a look at one more. The book doesn't do anything with non-polynomials in the text, so let's take a look at working with a transcendental function. Let's find all the points of intersection for the graphs of y equals cosine x and y equals x. So let's take a look at the graph and see what we can learn about the solution here. So there's the graphs of the two functions, not quite drawn to scale, the cosine and the line, and we can see that it looks like they only intersect in one point. So there's just going to be one point of intersection. So you only have to find that one intersection point. And we'll use Newton's method to do that. So the x-coordinate of this intersection point can be found by applying Newton's method to the equation f of x equals cosine x minus x. So the rationale here is we're trying to solve y equals x and find out an x value where also y equals cosine x. So we're trying to solve these two equations simultaneously. So we equate the y values to give us that equation. And if we can find x0 or a value x that does that, then we will have our x for which these two quantities are equal. So let's start Newton's method by finding a guess, an x0 value. So here's a close-up of the graph of y equals cosine x minus x, and we can see it crosses the x-axis down here. I guess we could zoom in and do better, but it looks like this happens at about 0.75, maybe a little bit to the right of that. So we can make a guess that x is about 0.75, and so we're going to use that value to be the start of our Newton's iteration sequence. So there's the x0. For Newton's method, we need that f prime term. That goes in the denominator. So we differentiate cosine x minus x, and we get sine of x minus 1, or minus sine of x minus 1. That'll be our denominator. And now that we have that derivative and we know what f is up here, we can apply Newton's method. The x1, the next guess, given by x0 minus f of x0 over f prime of x0. And let's see, we look up what f is to get the numerator. F was this function. So there's x0 put in for f. And down here we've evaluated the derivative at x0, again, which is 0.75. Again, use the calculator, and here's our result, 0.73911 approximately. Now we're going to use this value, this x1 value, as our input for Newton's method again, and that'll give us x2. So here's what x2 would look like. It'd be x1 minus fx1 over f prime x1. That. And then we just have to look up the x1 value we had before, 0.73911. There it is. And we put x1 into the numerator and the denominator for x. So here's the cosine x minus x term with our x1 in there. And here's the f prime, the minus sine x minus 1, again with the x1 value put in. Again, my calculator said this came out to be about 0.739085. So we have our list, x0, x1, x2. We could keep going on, but we're not. We'll just see how we're doing up to this point, but you could certainly go on and get x3 by using the x2 as input into Newton's method. So how are things looking? So let's just put these values x0, x1, x2 into cosine x0 minus x0. And the x0 value, we see that that difference comes out to be about 0.01, negative 0.01. That's not too bad. That's pretty close to 0. So we made a pretty good first guess. The x1 does better. We have 0 to 4 decimal places. And the x2, just a little refinement over x1, you can see there hasn't been a lot of change, but that one is really doing a good job. It is giving 0 to several decimal places. So again, we see these successive approximations give us evaluations that are closer and closer to 0. Okay. And of course, we could keep going if we wanted more approximations. Might be interesting for you to try this on your own, see what the next iterate would be by computing x3. As always, we want to answer the question asked. We ask for the point of intersection of the graphs of y equals cosine x and y equals x. We use Newton's method to find an approximation for the x-coordinate. That's about 0.739085. Because the intersection point of the two graphs lies on the line y equals x, we know that that intersection point has the same y-coordinate as the x-coordinate. And so we can answer the question by saying the intersection point is approximately equal to that value there. Okay. So this is a very easy method to use. I think it's a really clever use of the tangent line. And really, it's not something you have to memorize, because if you just understand the tangent line and the idea that all you're looking for is where a tangent line crosses the x-axis, then you automatically have the Newton's iteration formula at your fingertips. So go practice this with some of the My Math Lab homework, and hope you enjoy it. Bye.